Welcome to the Crazy Hat Chemist. We're doing another video on gases. In fact, it's the last video on gases here today. Bam! So today we're talking about the van der Waals equation. Okay? And watch the end of this video because I got the best hat today at the very end of this video. So you gotta wait for the hat. It's super cool. Okay? Alright. At high pressures, the gas molecule's volume is not negligible. Therefore, gas volumes tend to be slightly higher than that predicted by the ideal gas equation. At high pressures, attractive forces between molecules come into play at short intermolecular distances. This lessens the force that molecules collide with the sides of the container. Therefore, the gas pressure is less than that predicted by the ideal gas equation. These situations must be accounted for mathematically, and that's the van der Waals equation. Okay, so low volume, high pressure, and you can see that in this example of this apparatus that we did in the previous video. Okay, so van der Waals. This is the ideal gas equation. We've discussed this before, PV, and that's PV equals nRT. I want you to look very carefully at this. And what we are dealing with here is a correction factor for both the pressure and the volume. So the left-hand side of this equation is going to change, but the right-hand side, the nRT, the number of moles, the gas constant, and the temperature are going to remain the same. So the right-hand side is going to be unchanged. The left-hand side we are going to change. Okay, this is the van der Waals ideal gas equation here. Okay, you should see that there's a correction factor here for the intermolecular forces which reduce pressure. Okay, and then there's a correction factor here for the finite volume of gas molecules which increase the volume. Okay, that's right. That's why the reduced pressure, that's why you have to add it, and the increased volume, that's why you have to subtract it. Okay. For carbon dioxide, now each gas has its own set of two constants. A and B are constants for those specific gas molecules, whatever they are. So for carbon dioxide, the constant for A is 3.592 atmospheres liters squared divided by moles squared. And the constant for the B is 0.04267 liters per mole. These values you can look up in the Handbook of Chemistry and Physics, the CRC in other words. Okay? And they are specific for that particular gas, whatever it is. Okay? These are experimentally determined constants for each gas, and those units allow us to cancel out the units for this equation, so it ties in very nicely. All right, let's see how this is applied, and we're going to do a problem here. We're going to calculate the pressure difference using the ideal gas law and the van der Waals gas law. If 3.4 moles of oxygen is in a 1.7 liter tank at 25 degrees Celsius, and we have the two constants for oxygen that I looked up in the CRC. That is 1.36 atmospheres liters squared over mole squared for A, and for B it's 0.0318 liters per mole. So first we're going to do the ideal gas equation, then the van der Waals equation, and then we're going to take the difference of those pressures to figure out the difference of the two pressures. Now again, the ideal gas law is a great approximation under most circumstances, but the van der Waals equation really gives you what you really need under the perfect situation here, under all situations in other words. Okay? So I'm solving the ideal gas law for pressure. That's P is equal to nRTV, and I'm going to plug right into this. So I've plugged right into here. I've got my 3.40 moles of gas, of oxygen gas. I've got my gas constant. I got my 298, that's the 25 degrees Celsius, and I've got my volume at 1.70 liters. I'm going to solve for this, and I'm going to get the pressure under ideal conditions at 48.9 atmospheres. Okay, now what I'm going to do is I'm going to use the van der Waals equation and rearrange that to solve for pressure. Now this is a fun activity. I want you to do this and try to rearrange the van der Waals equation for pressure, and that's what you get right there. Now I'm going to plug the appropriate numbers into the places into this pressure of the van der Waals equation. And I've done that right here, maintaining the units right here. So on that left-hand side, you should see N, which is the number of moles, 3.40. I got the gas constant, that's 0.820 0.0821 liters atmospheres moles Kelvin, and the 298 temperature that's in the numerator. In the denominator, I got the volume on the left-hand side, that's the 1.70 liters, minus the NB. The N, okay, is in there, and the B is in there as well. The N is the number of moles as 3.40 moles, and then the constant for B, and you should see that the units are appropriate. Then there's a minus sign and then the other fraction, which is the N squared A over V squared. Okay, and you got 3.40 moles, that's squared, and you got that A constant for oxygen gas, that's the 1.36, divided by the 1.70 liters, and that's squared. And you're going to shove all this into your wonderful calculator, and you're going to get the following value for the pressure using the van der Waals equation, which is 46.8 atmospheres. So what we're going to do is we're going to take the difference between these values. So which one is the best value? Of course, the best value is from the van der Waals equation. The ideal gas law is a good approximation under most conditions. But the difference here is that it's 2.1 atmospheres less than expected. Okay, and the ideal gas law is a great approximation, but the van der Waals equation is really the one that you want. This is the last video in this series of gases, and I got a super cool hat. So I am done with this series of videos here, which is super cool. And someone asked me, hey, Mr. Marprion, when are you going to be done with the gas law unit? Okay, and I'm going to say, when pigs fly, I'll be done with that. Okay, don't wait for pigs flying to give me a thumbs up on that video or to subscribe to my YouTube channel. I'm going to see you next time for whatever the next unit is. I love you. Have a great day. Bye now.